好的，那我们现在开始来上课哈。We have come to the section of multiple hypothesis testing. So, in this session, rather than the binary problem we have talked about in previous chapters, we're going to do this multiple hypothesis. So, up to this point, we will say that we are going to choose the hypothesis that has the maximum likelihood. So, as you can see in this equation, what we have been doing here is that you choose HK, and of course HK is among the multiple hypotheses, meaning that HK could be H1, it could be H2, it could be anything in the hypothesis. But the point is, how should we say now H3 is the best? If I'm doing H3, then how should I argue H3 is the choice that that is going to give me the best performance? Then the idea is I'm going to say that H3 has the maximum likelihood among all those choices you had. So then I can say H3 is the best. Of course, in other examples, you may choose different hypotheses, but the point is you choose the one with the maximum likelihood. Okay, and then the other thing is if you have prior I'm sorry, to make a correction, this is called the M-ary. Notice this terminology, M-ary. M-ary meaning that you have hypothesis. Then maximum, which is understandable. A posteriori. A posteriori means that after observation. Prior means before observation, a posteriori means after observation. 所以这是专有名词，就是我们先前谈的 prior information，指的是在 observation 之前有的 information 叫 prior information。A posteriori 是这个好像是那个希腊文还是什么，从很古老的英文就有的一个字啊，所以不是正统的英文，但是它是从古老的希腊文还是什么传下来的。A posteriori means it has it is something after observation. Okay, so a posteriori is the decision that you do after observation. So we call it maxima a posteriori probability. Then it will be simplified as MAP. I like to explain this in such details because you're going to see this from time to time. 如果你在这个领域里面，不管你是在公司工作还是在学术领域继续做研究，你将会常常看到 ML、MAP、Bayesian 这些字，你就是会经常的遇到这样，所以这专有名词就是了解清楚哈。MAP decision rule. However, the prior are equal. If the prior are equal, then it will be something like this, right? This is just the basic. This equation is the basic probability identity, and then you see if they are equal, then this P of Hi becomes 1 over m. So the others are the same. And to maximize this thing, We only need to maximize this thing. We call this for different I, which term is different. Px is the same. In fact, Px is, after observation, it has been set like a constant. So it doesn't matter. P of x doesn't matter. P of x doesn't matter. 1 over m is the same. Then the remaining term is P of x conditional hi. Therefore, for equal prior, notice the word prior. For equal prior probability, we decide hk if px conditional hk is larger than px conditional hi for I not equal to k. In fact, I should say for all, you know the word for all, this uh, for all. There are notations that I use, right? This is exist, right? In terms of mathematical notation, this is, means exist. There exists something. This is for all, for every I not equal to k. Not just one I not equal to k, is for all I not equal to k. This equation sustains, then we will say HK is the best decision. This is the M-ary maximum likelihood decision. So this is the M-ary maximum likelihood. Finally, we will observe from 3.23 that to maximize P of x hi conditional x, we can equivalently maximize this thing since P of x does not depend on I. If you're deciding something over I and there's one thing P of x, see my cursor, P of x that is not dependent on I, then it's just a constant and we can eliminate it. So in fact, if you see this, we are maximizing this, well, we're in fact maximizing this multiplied by this, which is what we have here. Then P of x does not depend on I, right? That is obvious. Equivalently, the MAP rule maximizes this thing. Okay, we have this thing, but we take log of it, which we call monotonic transformation, right? Something to be maximized, then you take logarithm of it, you maximize it, they're equivalent. This is called monotonic because log function is monotonic. Okay, so you want to maximize this, then you maximize this, which is equivalent. All right. So an example that follows. Assume that we have three hypotheses. H0 is x equal to minus a plus w. H1 is just w, which is the noise only. In fact, I should say when something is only noise, it means that maybe the signal is zero. We can think of it that way, right? For example, I'm going to give you $0. $0 meaning I'm giving you nothing, right? It's the same thing. So when the signal is zero, it's equivalent to nothing here. Nothing. I'm saying look at my cursor here. Nothing here is equivalent to signal equal to zero. So that interpretation sort of gives you understanding of the signal structure. You have minus a, you have plus a, then you have something in the middle which is zero. All right, so Alright, so this, of course, then we do the same setting. Just we have page 83. Slow down a little bit so that you can follow by your textbook. So this A larger than 0 and Wn is Wgn with variance sigma squared. Furthermore, if the prior probabilities are equal, meaning that for each hypothesis they are equal, then the ML decision rule applies. Consider the first case of n equal to 1. We then have the PDF shown in figure 3.11, which we will see here. We'll come to see it in a little bit. By symmetry, it is clear that to minimize PE, we should decide H0 if this is smaller than minus A over 2, H1 if minus A over 2, minus A over 2 smaller than x0 smaller than A over 2, and H2 if x0 larger than A over 2. Okay, so for multiple samples, we cannot just plot the multivariate PDF and observe the regions over which each one yields the maximum. Instead, we need to derive a test statistic, the conditional PDF. The conditional PDF. So P of x conditional hi equal to this 1 over 2. This is what? This is again a multivariate. Recall in chapter 2 we talked about the multivariate Gaussian random variable, and this is a PDF for multivariate. How come it's multivariate? Because it goes from 0 to n. So we have n samples. Just a little bit of comment. If you go from 1 to n, it's the same thing. It's just the index difference. Okay, from 0 to n minus 1 is equivalent to 1 to the n. You have the, after all, they all have n samples. That's the point. From 0 to n minus 1 or to 1 to n, it's the same thing. Alright, so so we have the probability density function of this, and then of course you have this mean here, this mean, which is sort of a little bit different from previous example. You have multivariate, so you have this term, but you also have mean AI. In this case, it will be A, it will be this will be something like A0. This will be something like A1. A1 is 0, and then A2, which is A here. So A0 is minus A, A1 is 0, A2 is A. So to maximize this, we can equivalently minimize this thing. Minimize this thing. Because of what? Because you see, for each I, this is the same. This is the same. This is the same. So what remains is this term. The only thing that relates to I is this term. So in that case, we sort of like just minimize this is equivalent to minimize this. Okay, then we are happy. We are happy because that complicated equation now is simplified to this equation. And let's take a look at this. You have condition on H0, you have this distribution. Condition on H1, you have this distribution. Condition on H2, you have this distribution. Now we are setting threshold over here, minus A over 2, A over 2. Then we separate it into three regions. One is to decide H0, the other is to decide H1, and then the other is to decide H2. H2. Okay, so that sort of gives us a probability distribution under different circumstances. Then now we have also set the threshold and the regions and for each decisions. Now we kind of on the halfway to we are already at the middle of the discussion. So now we are slight using a slight manipulation. Manipulation means that you sort of reformulated and then simplified it. Manipulation 在数学里面的意思就是做一些数学上的调整、变数变换或者简化，就是大概就是这个意思。With the slight manipulation, then we express d I square like this, and then doing like this, and then doing like this, and simplified it. Eventually, we get something like this. So now it is now apparent that minimize this, we choose this for which AI is closest to X bar, closest to X bar. Therefore, we will decide X bar smaller than. Uh, Let me just clarify. X bar means sample mean. Okay, it's sample mean. It's just take the summation of the samples and take the average. That's the sample mean. If your sample mean smaller than minus a over 2, H0. If it's minus a to plus a over 2, then it's H1. If it's larger than a over 2, then it's H2. So now we come back to here. By intuition, we will say, hey, this is what I want to do. This is what I want to do intuitively, right? This is what I want to do. Now, mathematically, we prove it. We now say this corresponds to maximum likelihood. So it has a theoretical foundation. Now, we are not saying this by arbitrary argument, arbitrary, like just suddenly I come up with the threshold and I say this is what I want to do. No, not anymore. It has a foundation, and its foundation is maximum likelihood. So it's a good argument now. So this detector is a special case of the minimum distance receiver. Also, it is an example of an M-PAM communication signaling scheme for M equal to 3. So if you have a PAM system that has M equal to 3, usually in QAM system we have 2 to the something, like 2, 4, 8, but in some cases PAM you have M equal to 3, right? So now we have a decision rule. This is the decision rule, the most important thing, decision rule. Now we come up with it. And then now we want to decide the PE, the error probability, Now we have 6 types in general, and then therefore we will it'll be easier for us to decide the PC. PC is the probability of a correct decision. How come? Think about it. 6 types of error. What 6 types? Let's say the ground truth is H0. Then you're making a mistake for H1 and H2. That's two kinds of error. Now the ground truth is H1 and you're making decision for H0 and H2, the other two. Now you have 4 errors. Now the ground truth is H2. Now you're making decisions for H0 and H1. Now you're another 2 errors. So you have 6 types of errors. So to discuss errors is more complicated. Then how about let's just discuss the probability of correct decision. Seems to be easier, right? Probability of a correct decision. Therefore, the probability of correct decision is equal to summation of this P hi condition on hi, you are making hi multiplied by p of hi, okay, I from 0 to 2, and then 1 over 3 p of hi condition on hi, because the equal prior, but equal prior is not always the case. As I mentioned, in communication system it is mostly correct, but in other cases it may not. All right, and then continue on, you have 1 over 3 p probability of this equal to something, and of course then when you're making the decision for the second one, you have this in the middle, right? And then you have this larger than 2a over 2. And then we make out some Q functions, because condition, this is Gaussian distribution, right? Gaussian distribution has a Q function formulation, and you have Q function formulation, Q function formulation. At the end of the day, you get you do again some manipulation of the equations, you get PC equal to this thing. Alright, so at the end we get the probability of correct decision. Probability of correct decision. So that the error is 1 minus PC, right? Because the outcome has only two cases. One is correct, one is incorrect, which means error. So if you use 1 minus PE, 1 minus PC, you get PE, you get PE. So we're at page 85. So you get PE equal to this. Now, is it reasonable? Think about it from an engineering perspective. It is. How come? If signal strength, which means A, is larger, then you get larger numerator, you get smaller PE. That is reasonable, right? And then sigma square at the denominator, if you get smaller sigma square, you get larger for this factor, for this whole factor is larger. Now you are getting smaller PE. Is it reasonable? Yes, because the noise is smaller, then you get smaller PE. So it's all consistent with our engineering insight. Okay, so that, I think that'll be the end of the this session, and we are going to have another session, but this is the end of chapter 3, and we will continue on chapter 4. So let's take a break and come back later.